Hello and welcome. We are going to do some cleanup here for the nested quantifier section, and I'm going to just fill in the notes that we didn't get to during class. So let's take a look at this. So we want to express each of these as English sentences. And so for every, let's see, this is cuisine. So food type, cuisine. There is a student who likes that cuisine. It probably could be written a little bit more concisely than that, but that'll do it. Okay, for this next one, there is a cuisine that all students like. Okay, that's a little bit more concise, but it's not quite word for word. So let me just do the symbols one at a time here. Whoops, that's not what I wanted to do. No, not that either. I want this symbol. Okay, so here we are. Okay, so there exists a cuisine such that for all students, the student likes the cuisine. So I've just written it a little bit more concisely here. All right, onward. For all cuisines, there is a student, there are two students, such that one student likes the cuisine and the other doesn't. So that's what this means, is there is one who likes it, there is one who does not like it. Finally, there exists a student, there exist two students. Of students, if only I could write, such that for all cuisines, if one student likes it, the other does too. I suppose I should emphasize, there exist two different students. There we go. Because of that, there are different students. One student likes the cuisine, the other one does as well, and vice versa. I mean, technically that's one student likes the cuisine if and only if the other one likes the cuisine. So it's a little bit hard to write that because that's not the way that we speak in English, but that'll do it. All right, let's find some other notes that I didn't fill in earlier. There it is. Moving on to this page. I want to know if these two are logically equivalent. So notice that the order, this is kind of important, the order of the nested quantifier matters. So here, there exists a student such that for all cuisines, oh wait, this is no longer students and cuisines, is it? Oh, well, I guess since we don't have a specific predicate, we can use that. Why not? We can use let's use the predicate P of XY is that X likes Y. We'll use that predicate since this appears to be using the same domain for both of these. Okay, so there is a student who likes everyone. So that's what this means. Whereas this one over here, I know it looks like it's almost the same thing. All we've done is we've reversed the order of the predicates. But in this case, every student has someone who likes them. So here the emphasis is on the that you have for every y, every student, then you say, okay, well, what's special about all of these students? Well, each one of them, there is someone who likes them. Whereas over here, there exists one student, there is at least one, who likes everybody. So there's the difference. So these are not the same. These are not equivalent. The next one, these are equivalent. I won't go into the details here. I guess that as long as you have the same quantifier, you can switch the order of those quantifiers. I mean, this means everybody loves everybody or likes everybody else. And this means that they mean the same thing. And the same thing goes here. You can switch. These are equivalent. So those are equivalent and those are equivalent. So here you can switch the order as long as they're the same quantifier. Those can be swapped. So there is a student, and there are two students where one of them likes the other one. And this means exactly the same thing. You're just changing the emphasis, but it's the same statement. All right, let's go find the rest of the pages that we haven't done. Ooh, there's quite a few. Well, I'll do as many as I can endure. Okay, so there exists an integer. We want to write, let's see, using mathematical notation. And so here is, I just want to emphasize that when we're doing something mathematical, we don't need to make up a predicate for every mathematical expression. So using mathematical notation just means you can use inequalities or in sums and differences, whatever it is that it is. So here, there exists an integer. So there exists x in the integers that is not the perfect square of an integer. Let's see. So there is, so that, let me write this down. It is not true that x is equal to y squared. Such that for all y, okay, that works. So there is an integer that is not the perfect square of another integer. So here there exists some integer. For all other integers, it is not true that x is equal to y squared. Now the negation is that, let's see, and that's true. That is a true statement because I can just, the number 3 is not a perfect square. Okay, so the negation of this would be that for every x, for every integer, there exists another integer, and then we'll do the negation of the negation. So notice what I've done here is I instead of putting the negation over here, I moved it inside the parentheses, and so now you can just get rid of those. And so for every integer, there is another integer such that x is equal to y squared. That's not true. Because, well, 3 is a good example of why it's not true. Okay, every positive integer is composite. Okay, so for every integer, I'm going to do this to emphasize that it's the positive integers. So these are the integers greater than 0. Composite, what does it mean to be composite? It means that there exists a y and there exists a z. And what we want from this is that x is equal to y times z, and y is greater than 1 and z is greater than 1. That's really what it means for a number to be composite. It means that it can be factored into two other numbers, and that those numbers are both bigger than 1, because, of course, everything can be factored into. That is not true because prime numbers are not composite. So let's write the negation. And I'll use the same trick as I did above. I'm just going to change all of the quantifiers until I get into the statement, and then I'll negate the statement. So instead of a for every, there's a there exists, and then for every y, and then for every z. Now I have to negate this thing. I'm going to be using the De Morgan's law. So let's see. Yeah, this is a weird way of doing this, but I'm going to do it anyway. So let's see, the negation would be that x is not equal to yz, or the negation of this is that y is less than or equal to 1, or z is less than or equal to 1. Okay, that works. So negation is that there is an integer such that for all other integers, either x is not the product of y times z, or either y or z is less than or equal to 1. So that is a true statement. So this one is not true. Not true. And this one is true. And in particular, pick a number like 3. 3 is not going to be the product of any two integers unless, one of those integers is equal to 1. Okay, great. Let's see, write the following statements in logical symbols, then write the negations. Okay, every student, and what are we doing here? We're using students, homework assignments, problems, and we have these predicates. Okay, so for every, let me change colors, I'm sick of that color. For every student has solved at least one problem, there exists a problem on every homework. Oh, okay, let me back off. Let's try again. Okay, so even though in English we've got every student first, and then we have at least one problem, notice where those problems are coming from. They're coming from every homework assignment. And so for every student, for every homework, there is a problem. So this is we just to keep things straight. This is the way that this English would be translated, and then what's going on? Well, it turns out that that let's see, the solving. So student X has solved problem Z, and problem Z is on homework Y. Okay, now what else do we want to do? I guess I've gotten myself into this, right? It's the negation in symbols. So the negation, so that's the statement. The negation is going to be there exists X, there exists Y, for every Z, and then we negate both of these. So the negation of S xz, or the negation of I in zy. Do I have to write that in plain English? I hope not. Express the negation in English. Okay. I'm just going to say it instead of writing it. There is a student and a homework assignment, so that for every problem, either the student did not solve that problem, or that problem is not on the homework assignment. In other words, there is a student who didn't solve any of the problems on at least one homework assignment. All right, every student in the class has solved all the problems on at least one homework assignment. Okay, so for all students, there is at least one assignment. So each student has so it could be a different assignment for each student, that's fine. So that for all the problems, Z, what do we know about these problems? Well, this student has solved the problem, and that problem is on that assignment. Okay, the negation of this would be, so the negation, there exists for all, there exists the negation of S, X, Z, or the negation of I, Z, Y, very similar to what we had above. In plain English, this would be that there is a student who, for every homework assignment, there is at least one problem on that assignment that this student has not solved, essentially. That's what this says. So, yeah, in other words, yeah, that there's, yeah, okay. Is this it? No, there's more. Some student in this class has solved all the problems on every homework assignment. All right, that's easy enough. There is a student, so that for every problem, you know, I don't know that we need to reference the homework assignments because we're just every single problem. I think that would do it. Yeah, just this student has solved the problem. Yeah, I don't think we need to reference the homework assignments because the domain is problems. Problems, where are the problems coming from? I'm guessing that they're from the homework assignments. So, I mean, if you really want to be complete with this, I suppose we could throw in the homework assignments as well. You know, just slide this over. Yeah. Here, let's do this. Call this homework assignments. And then this problems. Okay. I guess that here, just in case there are additional problems, we'll do this. If the problem is on one of the homeworks, then that student has solved it. So, negation. For every student, there exists a homework assignment, and there exists a problem, so that either negation of this. That would mean that this is true. And this is not true. There we go. All right, I'm moving on. Okay, I want to write this with quantifiers, logical connectives, and mathematical symbols. The sum of the squares of two integers is greater than or equal to the square of their sum. So for every integer, you know, I'm going to use, I think I'm just going to do it this way, x, y, and z. There we go. No, I don't even need the z, do I? So as long as I have two integers, So for every x that's an integer, for every y that's an integer, so we can just go with this. For every x and y in integers that are integers, it is true that, let's see, the sum of the squares, x squared plus y squared is greater than or equal to x plus y squared. The sum of the squares of two integers is greater than or equal to the square of their sum. That is not true. Well, it doesn't say that they are. So that's not a true statement, by the way. You can pick three integers, or two integers, 1 and 2. 1 squared is 1, 2 squared is 4. 1 plus 2 squared is 9. So, that's the triangle inequality says the opposite. It says that it's less than or equal to. Anyway, getting back to this, the difference of two positive integers is not, so this is not true. Not true. Difference of two positive integers is not necessarily positive. Okay, so for all, not necessarily. So there exists x and y, which are integers, so that x minus y is less than or equal to 0. Yeah. I think that does it. That one is true. Okay. Oh, sorry. Have to specify that we're talking about positive integers here. Okay, let's translate into English here. There is a integer, real number that can be added to any number, and the result is the number. That is not very good. So this is basically that there's an additive identity. That's what that's saying. And then here, for every integer, if two integers are both negative, then their product is positive. All right, I think we've got to be, we're almost done. Good. Not everyone in this class is on Discord, so there is someone, X in this class. I'll just say that here, let's say that we've got Discord C, D for Discord. How about, and C chatted. Okay, we're just going to assume that we're domain, the domain E students in this class. Okay, so there exists a student in this class who is not on Discord, such that the negation of D of X. Someone in this class, so there is someone, is on Discord but has not chatted with anyone else in this class. Okay, well then for everyone else, let's see, this person is on Discord and they have not chatted with anybody. Okay, there is a student in this class who has chatted on Discord with everyone else in this class. Okay, so then for every other student in this class, they have chatted How about that? No student in this class has chatted with everyone else on Discord. Okay. So that means no student means that there's everybody. This is going to be true for everybody. For all students in this class, there exists another student in this class where the first student has not chatted with the other one. Everyone in Discord has chatted with at least one other student in this class. Okay, so for everybody in this class, there exists another student in this class, so that as long as the first student is on Discord, they have chatted with someone. Everyone in this class except one student is on Discord. Okay, how about this? Let's see. There exists a student. That will be our unique student who is not on Discord. For every student, the following is true. The first student is not on Discord. And how am I going to say this? Everyone else is on Discord. So as long as X and Y are not the same person, then this other person is on Discord. Wow, lots of parentheses there. And then finally, there are two students in this class. Okay, here's the first student. Who between them have chatted with everyone else in this class. Okay, so let's get everyone else. So that means that either person X has chatted, or, or person Y has chatted. Or both. All right, that does it. Hopefully this helps you, and I hope you have a great snow day.